Welcome to our comprehensive masterclass on Retrieval-Augmented Generation, or RAG, and its critical role in modern AI agent architectures. In this series, we'll break down the core concepts, practical strategies, and real-world applications that make RAG, vector databases, and advanced chunking techniques essential for production-ready AI. Whether you're an engineer, product manager, or AI enthusiast, this journey will help you understand how to build smarter, more reliable, and context-aware systems. Let's start by exploring what RAG is and the fundamental problem it solves in real-world deployments. Retrieval-Augmented Generation, or RAG, is an architecture that enhances the output of a large language model by referencing an authoritative external knowledge base before generating a response. This approach addresses the limitations of static knowledge cutoffs, internal biases, and hallucinations by grounding the model's answers in verifiable real-time data. For example, imagine an internal HR assistant that needs to answer questions about a company's health insurance policy updated just yesterday. Instead of retraining the model every time a document changes, RAG searches the latest PDF and injects the relevant clauses directly into the prompt. Chunking is the process of breaking down large bodies of text into smaller, meaningful segments. Even though modern language models can handle long context windows, passing an entire 200-page document directly can cause high latency, increased costs, and the risk of missing critical details buried deep in the text. For instance, processing a country's entire legal tax code for a simple query about capital gains tax would be inefficient and expensive. Instead, chunking extracts only the relevant paragraphs, making the system faster and more cost-effective. There are different ways to chunk text. Fixed-size chunking splits text strictly by a set number of characters or tokens regardless of context. This can lead to awkward splits like cutting a sentence in half. Recursive character text chunking, on the other hand, uses a hierarchy of separators, paragraphs, sentences, spaces, and characters to split text more naturally. It ensures that sentences and paragraphs remain intact, preserving meaning and context. For example, a recursive chunker would keep a full paragraph together, while a fixed chunker might split it mid-sentence. Chunk overlap is a technique where a portion of text from the end of one chunk is duplicated at the beginning of the next. This ensures that important concepts spanning across chunk boundaries are captured together, preventing data fragmentation. For example, in a medical manual, if one chunk ends with a treatment recommendation and the next starts with the medication details, overlap ensures the relationship is preserved in at least one search result. This technique is crucial for maintaining semantic continuity in vector searches. Dense embeddings are high-dimensional, continuous vectors generated by deep learning models. They capture abstract semantic meanings, themes, and conceptual synonyms. Sparse embeddings, in contrast, are vectors where most values are zero, focusing on exact keyword matching and frequency. For example, searching for feline illnesses with a dense embedding would match cat diseases semantically, while a sparse embedding would look for the exact words. Both methods have their strengths, depending on the search requirements. Structural-aware or syntax-based chunking leverages the native layout of documents, such as Markdown headers, HTML tags, or JSON keys, to split data at logical section transitions. This method ensures that related information like a subheading and its bullet points stay together in the same vector node. For example, when parsing technical documentation, this approach prevents instructions from being separated from their titles, maintaining the integrity of the information. Semantic chunking uses machine learning or distance metrics to find natural breakpoints in text based on meaning. It calculates the similarity between sentences and splits the text when the similarity drops below a threshold, indicating a topic shift. For example, a podcast transcript parser might split the text when the conversation moves from early childhood education to venture capital investing. This approach ensures that each chunk is topically cohesive. Errant document retrieval, also known as small-to-large chunking, involves splitting a document into small child chunks for precise searching and linking them to larger parent documents. When a query matches a child chunk, the system retrieves the entire parent context for the language model. For instance, if a financial analyst asks about Q3 growth, the system finds the relevant sentence and provides the full financial table and surrounding paragraph, offering comprehensive context. Retrieval bottleneck refers to the performance limit imposed by the quality of the data retriever in a RAG pipeline. If the vector database or semantic search fails to surface the most relevant information, even the most advanced language model cannot generate accurate answers. For example, if a support bot is asked how to cancel a subscription but retrieves only privacy policy chunks, it won't be able to help the user, no matter how sophisticated the model. Bounding means restricting a language model's output to rely strictly on facts provided within the prompt context. This is enforced through system prompts that constrain the model's behavior and provide explicit instructions. For example, you might set a prompt that tells the assistant to answer only using the text inside specific tags, and to admit when information is missing. This practice ensures factual accuracy and transparency in AI responses. Mathematically optimizing chunk sizes involves creating a synthetic evaluation dataset of query context pairs and testing different chunk sizes and overlaps. By calculating retrieval metrics like context recall and precision, you can select the smallest chunk size that maximizes recall without sacrificing speed. For example, an e-commerce team might find that 512 token chunks yield 94% accuracy, while smaller chunks drop performance due to sentence splitting. Encoders and cross-encoders are two approaches for matching queries to documents. Encoders embed queries in documents independently, allowing for rapid similarity calculations. Cross-encoders, however, process the query and document together, achieving higher accuracy but at a greater computational cost. In practice, a system might use a biencoder to narrow down candidates and a cross-encoder for final ranking, balancing speed and precision. Hierarchical node parsing organizes documents into a tree structure, with chapters as parents, sections as mid-level nodes, and paragraphs as children. This structure maintains relationships between segments via metadata links. For example, if a search matches several paragraphs about API endpoints in the same module, the parser can roll them up and present a single, clean overview to the language model, improving clarity and relevance. Metadata filters are structured properties, such as creation date, user ID, or category attached to vector objects during ingestion. These filters allow the database to partition and ignore irrelevant vectors before or during similarity calculations. For instance, in a multi-tenant application, a department filter ensures that only relevant documents are searched, improving both speed and accuracy. Understanding the token-to-character ratio is critical when structuring ingestion chunks. In English, one token is roughly 4 characters or 0.75 words. Embedding models enforce token limits while text slicers use character counts. For example, if a model has a 512 token limit, splitting text at 2048 characters helps avoid truncation errors, ensuring smooth processing and accurate embedding. Naive sentence-based chunking splits text at every period, exclamation point, or question mark. The main downside is the loss of anaphoric references. Pronouns like it or they become disconnected from their subjects. For example, splitting the Tesla Model Y incorporates a specialized heat pump. It improves efficiency, leaves it without context, making the embedding less useful. Query rewriting is a foundational step in advanced RAG systems. It uses an upstream language model to transform ambiguous or shorthand queries into fully articulated, descriptive prompts optimized for vector search. For example, if a user asks, "How do I fix the error from yesterday?" the system rewrites it to troubleshooting steps for Docker container exit code 137 out-of-memory error, ensuring more accurate retrieval. Document transformation sits between raw text extraction and chunk embedding. It cleans and enriches data by removing boilerplate markup, translating languages, normalizing text, or generating summaries. For example, a web crawler might strip out HTML sidebars and footers, leaving only the instructional content for embedding. This step ensures that only high-quality, relevant information is processed. Markdown-aware chunker scans text for structural markdown indicators like headers and dividers. Instead of splitting at arbitrary points, it groups content logically by heading hierarchy, ensuring that sub-bullets and code blocks stay with their relevant headers. For example, in a deployment guide, a code block remains attached to the step it explains, preserving instructional clarity. RAG and fine-tuning are two distinct approaches. RAG injects external information into the prompt at inference time without changing model weights. It provides auditable citations and updates instantly as the database changes. Fine-tuning, on the other hand, adapts the model's internal memory by training on new data, which is ideal for style or vocabulary but is slower and less flexible for updating facts. For real-time accuracy, RAG is preferred. Deploying RAG in production environments means integrating it with real-time data sources and ensuring robust retrieval pipelines. This allows AI agents to answer questions using the latest available information without the need for constant retraining. For example, a customer support bot can reference updated policy documents instantly, providing accurate and timely responses to users. Vector databases are specialized storage systems designed to handle high-dimensional vector data, such as embeddings from language models. They enable fast and efficient similarity searches, which are essential for RAG pipelines. By indexing and retrieving vectors based on semantic similarity, these databases power the retrieval step that feeds relevant context to language models. Similarity search is the process of finding vectors in a database that are most similar to a given query vector. This is typically done using mathematical operations like dot product or cosine similarity. In RAG systems, similarity search ensures that the most relevant chunks of information are retrieved and passed to the language model for response generation. Context window refers to the amount of text a language model can process at once. While modern models have large context windows, they are still limited. Chunking and retrieval strategies are necessary to ensure that only the most relevant information is included, optimizing both performance and cost. One of the main benefits of RAG is its ability to reduce hallucinations when a model generates plausible but incorrect information. By grounding responses in real retrieved data, RAG ensures that answers are based on facts, not just model predictions. This is especially important in domains like healthcare, finance, and law, where accuracy is critical. Passing large documents directly to a language model can result in high latency and increased costs due to token limits and processing time. Chunking and efficient retrieval minimize these issues by ensuring only the necessary information is processed. This makes RAG systems scalable and cost-effective for enterprise use. The lost in the middle phenomenon occurs when important details are buried in the middle of a long prompt and are missed by the model. Chunking helps avoid this by extracting and highlighting only the most relevant segments, ensuring that critical information is always included in the context window. Granular semantic search involves breaking documents into fine-grained chunks such as sentences or paragraphs and embedding them for precise retrieval. This allows the system to match queries with highly specific information, improving the relevance and accuracy of responses. Maintaining context across chunks is essential for accurate information retrieval. Techniques like chunk overlap and hierarchical parsing ensure that relationships between concepts are preserved, allowing the language model to generate coherent and contextually accurate responses. Evaluating the quality of retrieval involves measuring metrics like context recall and precision. By testing different chunking strategies and database configurations, teams can optimize their RAG pipelines for both speed and accuracy, ensuring that users receive the most relevant information. Automated evaluation scripts can run across large datasets to test different chunk sizes and overlaps. This helps teams identify the optimal configuration for their specific use case, balancing retrieval accuracy with system latency and resource usage. One of the strengths of RAG is its ability to update instantly as new information becomes available. By changing the content in the vector database, the system can provide up-to-date answers without retraining the language model, making it ideal for dynamic environments. RAG systems can provide auditable citations by referencing the exact source of retrieved information. This transparency builds trust with users and allows for easy verification of answers, which is especially important in regulated industries. Advanced RAG systems handle ambiguous or shorthand queries by using query rewriting and context analysis. This ensures that even vague questions are transformed into precise search prompts, improving the likelihood of retrieving the correct information. Before embedding, raw data must be cleaned to remove irrelevant content like navigation headers, trackers, or cookie banners. Document transformation ensures that only high-signal relevant information is processed, leading to better retrieval and more accurate responses. Document transformation can also include language normalization, such as translating content or standardizing text formats. This step ensures that all data is consistent and ready for embedding, regardless of its original source or language. Generating summaries of complex sections during document transformation can help create more concise and focused chunks. This makes it easier for the retrieval system to match queries with the most relevant information, improving both speed and accuracy. Chunking strategies that respect document structure like Markdown-aware chunkers ensure that sections, sub-bullets, and code blocks remain together. This prevents important instructions or details from being separated, maintaining the integrity of the information. With RAG, updating facts is as simple as changing the content in the vector database. There's no need for expensive and time-consuming model retraining. This makes RAG ideal for environments where information changes frequently, such as news, finance, or policy. While RAG is best for dynamic, factual updates, fine-tuning is useful for teaching a model specific styles, tones, or specialized vocabularies. Combining both approaches allows you to build AI agents that are both knowledgeable and contextually appropriate for your domain. RAG and vector databases are used in a variety of real-world applications, from internal HR assistants and customer support bots to financial analysis tools and technical documentation search engines. These systems deliver accurate, up-to-date information, improving decision-making and user satisfaction. By leveraging RAG, vector databases, and advanced chunking strategies, you can build AI agents that are not only reliable and accurate but also transparent and auditable. These best practices ensure that your AI solutions are robust enough for production environments. Summary: mastering RAG, vector databases, and chunking strategies is essential for anyone building advanced AI agents. These techniques solve real-world challenges like static knowledge, hallucinations, and inefficient retrieval, enabling smarter, more context-aware systems. Remember to focus on data quality, retrieval accuracy, and system transparency for the best results. Thank you for joining this masterclass on RAG, vector databases, and AI agents. To continue your learning, explore hands-on tutorials, experiment with different chunking and retrieval strategies, and stay updated with the latest advancements in AI. Building production-ready AI is a journey. Keep iterating, testing, and optimizing for the best outcomes.